All right, I think I've got all, think I hit the checklist. All right, good morning, everyone. I have a special treat for you today. We're going to talk about the work of Archimedes. And it's well known that Archimedes is the great forerunner, among many other things, of the integral calculus. But we'll see, he even does much more than that. And I think we left off here with the result that we saw in the very first lecture, that he takes a parabolic segment and takes a very natural triangle from that segment. By natural, I mean he finds a point on the segment in which the tangent line is parallel to the base of his segment, and he uses that point to create a triangle. In that sense, it's a very natural kind of a mathematical point. It's not just some arbitrary point anywhere on this curve, but he picks the point that will give him a parallel tangent line. And that triangle there turns out to be a simple percentage of the entire segment. He's able to show that the entire segment is 4/3 the area of that big triangle enclosed. And we talked about this in the first class. We gave an indication of how that proof went in terms of a geometric series. Let's take a look at that series now. As he builds up his triangles from the first interior triangle there, T, which is going to be turned out to be 3/4 of the entire area. He creates the same kind of triangles with the same kind of structure, looking for points. A point here, which the tangent line will be parallel to this line, and looking for a point here in which the tangent line will be parallel to this line. He repeats this over and over again, creating smaller and smaller triangles, stuffing this in. Obviously, very, very much the same idea as our dumb rectangles given the calculus, where we're not being clever in terms of finding these wonderful triangles using this geometry and finding a progression that you can use to actually find the sum. No, in the calculus, we don't do any of this. We take the same old dumb rectangles and just make them thinner and thinner, and ultimately rely upon the fundamental theorem of calculus to actually give us the result. Yes, if you do add up the rectangles, you will get something closer and closer, but generally there's no easy way to do that. You have to find another way, and that's the fundamental theorem of the calculus, working with the antiderivative. So yes, the calculus goes way beyond where Archimedes is here, but the basic idea of exhausting the area of a curved area by using figures of straight lines that we do know the area of, and finding some kind of a regression, some kind of an algorithm which will allow us to calculate that ultimate area, that is integration. Okay? That is essentially the idea of integration. So to look at the progression that Archimedes finds, he starts with the area of the big triangle T, and then he's able to show that these two other green triangles, they turn out to be 1/8 of T. And then those yellow triangles, which again, there are 4 of those, he shows that they are T to 8 squared, 1/64 of the original T. And there are 8 triangles of the red, and they are T over 8 cubed. So he's able to derive this progression. We don't have time to see how he does this. This would take us quite a bit of intensive algebra. But if we factor the T out, we're left with a series. Notice that's 2/8, and then 2/8 squared, and then 2/8 cubed, and on. And 2/8 is nothing more than 1/4. So we have this series very much like the one that we saw in Zeno, where we went halfway to the wall, and then we had to go halfway again and halfway again, where we added up a half plus a fourth plus an eighth plus a 16th. There we had the powers of a half. squared and a half cubed. Now we have a fourth instead of a half. And we're going to use the same trick to calculate that infinite series. We'll call it S for sum. It's T times S. S is this infinite sum. And the trick is just with the Zeno, we multiplied by 2. Here we multiply by 4. When we multiply that series by 4, notice that we get 4 plus the repetition of the series. 4 times all those terms reproduces the term in front of it. And so 4S is nothing more than 4 plus S. We have reproduced that infinite series in the back. Easy enough to solve for S. Subtract S from both sides and divide by 3. Yeah, and so S here is equal to 4/3. Remember the Zeno of 1/2, 1/4, 1/8, 1/16, that equaled 1. Here, summing up of the powers of a fourth, we get something larger than 1/4. But we've agreed that the area of this parabolic segment is T times this S. And so therefore the area of the segment is 1/4, which is S times T. And that's his theorem. Okay. So Archimedes is just a master at this kind of exhaustion that we see here. And he winds up with such beautiful results. Again, that those Pythagorean simple fractions of 4/3 as opposed to some crazy decimal. Why is it that given this very natural mathematical triangle, the one that you get when you write the tangent, which is parallel to the dot to dot, not some arbitrary one. If you pick this very clever triangle to start with, you get this very, very simple result for a rather complex area, this area bounded by a curve, and of course the bottom straight line. So it's very Pythagorean, kind of very beautiful result of that simple fraction of a 4/3. And the heart of it is that calculation of that infinite series. We will see this more and more. The idea of adding up an infinite number of terms becomes an important factor, an idea in the development of the calculus. We can't go too much into it. We're focusing more on derivatives and integrals. This is kind of a third aspect of it, but we will make a nod here or there to where some of these infinite series pops up in our story. Okay, another piece of mathematics that Archimedes develops is called the volumes of revolution. He takes a rectangle, okay, like this purple rectangle that I show. It has a certain length of h and a certain width of r. And what he wants to do is he wants to revolve that rectangle around the x-axis. Okay, because it wouldn't be an x-axis to him, it would be just a line, just be the axis of his diagram. But notice when you revolve it around, you get a cylinder. And he wants to be able to show what the area of that, what the volume of that cylinder is with respect to the area of that rectangle. The rectangle is sweeping out the volume, so there should be some way to calculate the volume from the figure which is sweeping it out. And these are called volumes of revolution. Archimedes is the first one to do this kind of thing. He uses the method of exhaustion, and he plays around with rectangles, with triangles. If you spin a triangle around, you will get a cone. And if you take a semicircle and spin that around, you will get a sphere. Okay, these are classic problems in Calc 2. Calculus students learn how to do this using modern integration. Archimedes does this with the method of exhaustion. Okay, here's another variation on the same theme, taking now a parabola, that gray segment there, taking the parabola and spinning it around the y-axis, spinning around a vertical axis, you will get a paraboloid, you'll get a nose cone. And again, there should be some way of figuring out the volume of the nose cone from the area of the parabola, which is doing the spinning. Okay, and Archimedes develops this mathematics for the first time using the method of exhaustion. Here is just an indication of the idea of breaking up those areas into small pieces and spinning these simple pieces around and then adding up the pieces using the method of exhaustion. Again, a forerunner of the integral calculus. Taking that, area there of the kind of the cylinder that's being created in the spinning, he's able to show again one of his very beautiful results. What's the area of that parabola that's spinning around, making the nose cone? We'll take a look at the entire volume of the cylinder that the parabola is sitting in. Okay, the volume of a cylinder is the area of its base times the height. Well, if the width of the cylinder, width of the parabola up on top, we call r, then we're making a circle of radius r. So the base of the cylinder and the top of the cylinder would be pi r squared. That would be the area of the top and bottom of the can, and the height, of course, is h. He's able to show using the method of exhaustion that the nose cone is 1/2 of that volume. Another one of those simple ratios, which is not at all obvious why that would be the case, but he's able to prove theorems like this from the method of exhaustion. And you can see where this can go once we talk about functions and any kind of curve not being restricted to simple things like straight lines and simple curves like the semicircle. But once we get all kinds of curves and we start spinning those around different axes, we can get all kinds of shapes. And like I say, these are the problems like one there down the bottom are classic problems that all students of Calc 2 take. And you veterans of Calc 2, I'm sure, if nothing else, vaguely remember the idea of the volumes of revolution, even though you may not recall the algorithms that are used to solve them. Just one other thing to mention before we move on in terms of volumes and areas of shape. Archimedes, using the method of exhaustion, was able to find the area of an ellipse. An ellipse can be characterized by two numbers, the length of the ellipse and the maximum height of the ellipse. Traditionally, this is called A, this length here, and this length here is called B. And using the method of exhaustion, Archimedes was able to show that that area is pi times AB. What's interesting about this is, of course, we know that the ellipse is that the circle is a special case of the ellipse. When do you get a circle? You get a circle when A and B are equal, right? When the diagonal across is exactly the same as the diagonal up and down. And notice that if A and B are equal, the area of that figure, of that circle ellipse, would be pi times A, b pi a squared, where A is the radius. And so Archimedes truly has developed a generalized formula from the circle. And he proves this again using the method of exhaustion. Okay, we're going to spend some time talking about his measurement of pi. And he, in his work on the measurement of a circle, that's the name of the work that comes down to us, he proves what's called proposition 1, which we'll see over and over again in our talk. He says that the area of a circle is equal to the area of a certain triangle. Yeah, he's going to create a quadrature of the circle. Remember, a quadrature in the Greek mathematics is to turn a figure which has curved boundaries into a figure which has only straight boundaries. And ultimately, any figure with straight boundaries can be turned into a square. And that's where the quadrature comes from. It's easy enough to take this area of a triangle, double it, and get the rectangle. You just lay the triangle up on top. And I've already shown you in the last presentation that you can turn a rectangle into a square. So once you turn this curved figure into any kind of a straight figure, a couple of more steps will turn it into a square. So we just stop at the quadrature here when you get a nice figure like a triangle. This is the first time in history that anyone is able to do this, to take the area of a curved figure, and he's working with the simplest of all, start from the beginning. He's going to turn it into a figure that we do know how to find the area of. And it's a really incredibly beautiful result. He says that the area of the triangle you want to use is take the circumference and lay it out straight. Lay the circumference out straight, use that as your base, and use the radius as the height. That area of that triangle, which we know is 1/2 the base times the height, will be the area of this circle. Okay. The area of the circle will equal the area of the triangle, T, which is 1/2 the base, C, circumference, times the height, which is R. Okay, that's his proposition. So let's see how he does this, how he proves this. In the work, he just begins stating things and proving things, and he does assume that the reader knows from Euclid that the diameter of a circle is proportional to, the circumference of a circle is proportional to the diameter. Like given any two circles, the circumference to its diameter is the same as the circumference of the other circle to its diameter. And that constant of proportionality, as we now call it, is pi. So the circumference, turning a proportion into an equation, the circumference is equal to this constant proportionality times the diameter. We can write the diameter as 2 times the radius. The proportionality of constant we now call pi. And so we get the formula for the circumference of a circle, 2 pi r, a very familiar formula. He assumes that the reader knows this. Okay? He assumes that the reader knows it's Euclid. Because the symbol pi is not used. The symbol pi is not used for 2,000 years. But everyone knew that there was this proportionality constant, and they knew it was about 3. The Babylonians and the Egyptians knew it was about 3. So what's his idea? His idea to find pi is this constant, is to work with hexagons and octagons and regular polygons, both inside and outside of the circle. And the more sides that you take, the perimeter of these figures will get closer and closer to the perimeter that we want. Okay, and let's just prove this little formula that the area of a endergon of n sides is equal to 1/2 the height times the perimeter, which is n times s, s being the length of any side. Proof is really very easy. Okay, what is the area of the endergon? Well, just we have n of these triangles. Just add up the area of the triangles and multiply it times n. So the area of the triangle, of course, is 1/2 the base times the height, 1/2 the base, which is s, times the height, which we're calling h, and just do that n times. There are n of these triangles for a figure of n sides. But if you bring the n inside, we have 1/2 the height times n times s, but isn't n times s the perimeter? Okay, isn't n times s exactly the sum of adding the sides n times? So we have a nice little formula that he is going to use, that the area of these endergons is 1/2 the height that it goes out to times the perimeter. We'll be using that. And the other thing that he used, which we saw from the last time, is that you make these regular endergons of larger and larger size. Clearly, the area is getting closer and closer to the area of the circle. And in fact, the perimeter of these figures are getting closer and closer to the circumference of the circle. Okay. So as the number of sides of these endergons get larger and larger, the area does grow larger and larger. And the inscribed in circle, these areas get as close as you wish to the area of the circle. Okay. This again, is proved in Euclid in book 12. This is essentially the method of exhaustion to show this. That you can get as close to the area as you like by just picking n big enough. Okay. If you want the area to be just a, 1 over a googolplex, shy of the area, just pick n to be very, very, very large, and you'll find the Endergon to be rubbing right up against that circle to be less than that area of it from the area of the circle. We can get as close as we wish. Any degree of closeness, we can do it by picking n large enough. Okay? That comes from the method of exhaustion that's proved formally. He assumes that his readers know Euclid, know book 12, and know this fact. He's now ready to prove his theorem. I'm sorry, one more point. Whatever we say about the inscribed endergons is also true for the circumscribed endergons. Just that now we're getting our areas and our circumference, our perimeters closer and closer from the outside. They're all larger than the area of the circle and the circumference circle, but they're getting smaller and smaller because they're getting tighter and tighter around it, getting as close as you like to that area and circumference of the circle. Okay. So we're ready for our proposition. The area of a circle with a radius r and circumference c equals the area of a right triangle whose height is r and whose base is c. That's his theorem. That is, the area of the circle A is 1/2 r times c. He calls that T the area of the triangle. The proof is a double reductio ad absurdum. Sounds very complicated. It's not. What he's going to show is that there's no way for it not to be the case. That if you tell me that the area of the triangle is less than the area of the triangle, I'm going to show that that's impossible. I will reduce that to the absurd. There's no way that the area of the triangle can be less than the area of the circle. I'm then going to turn around and say, if you think that the area of the circle could possibly be bigger than the area of the, I'm going to show that that's absurd, that that can't be the case either. It's impossible for that to be the case. Therefore, there's only one case left. When you do the double reductio ad absurdum, when you show both things, both the greater case and the lesser case are impossible, as Sherlock Holmes would say, then the only thing that you can conclude is that what's left is what is true, that in fact the area of the triangle is equal to the area of the circle. Let's just do 1/2 of the proof. We'll just do the smaller, the inscribed endergons. So we're going to show that the area of the endergons can't be, the area of the triangle can't be less than the area of the circle. Notice that not only are the areas of all these endergons less than A, okay, that's visually the case, right? You go inside each one, you have area outside excess, which, the circle is not enclosed. The circle is outside of those straight lines. So yes, the area of the endergon is bigger than the area of the circle. We can see that. But also that the area is also less than T. The area of the endergon is less than the area of the triangle. Why is that? What's the area of the triangle? The area of the triangle is 1/2 r times c. Okay, that's how we constructed this triangle. We constructed the triangle by making the base the circumference and the height the radius. So the area of the triangle is 1/2 height times base. Well, look at the area of the endergon, which we showed in the last slide. It's 1/2 the height of the triangle times the perimeter. But isn't every single height less than the radius? Isn't every single height less than the radius all the way out? And isn't every single perimeter less than the circumference? So this number is less than this number, and this number is less than this number. And certainly 1/2 of the product is less than 1/2 of that product. Every single area of the endergon is also less than that triangle. And that's what he needs. He needs That fact and the fact that we can get closer and closer to show that it can't be the case, it cannot be the case that the triangle can be less than the area of the circle. So let's see why. Let's assume that the triangle is less than the area of the triangle is less than the area of the circle. I'm going to show, Archimedes is going to show that this is impossible, that this will lead to something which we know is false. And the idea of the reductio ad absurdum, if you start with a premise and you use valid logic and come up with something which you know is false, and your logic is correct, there is only one thing that you can conclude, is that your premise was wrong. We're going to start with the premise that the triangle is less than the area of the circle, and we're going to show something which we know is false. Here we go. Let us take a look on the number line of the area of the circle and the area of the triangle. Okay, there's a distance between them. The area of the triangle, we're assuming, is less. It's further down on the number line. Okay. All right. All you have to do now is pick n large enough so that the area of the endergon falls in between. Remember, we said that we can pick n large enough that we can get as close to the area as we like. We can get closer than the triangle. This triangle that you're saying is less than the area by some amount. Once you pick that amount, you're dead. Because once you say that the triangle is this less than the area, then I'm going to give you an endergon which is closer to the area of the circle than the triangle. But we've already agreed that the area of all the endergons are less than the area of the triangle. We know this. We know that all those heights are less than the radius. All its perimeters are less than the circumference. All of the endergons are also less than the triangle. You can't put an endergon in between T and A. But once you make T less than A, you're giving me room to get closer to A than T. Once you've given me room to get a place in between T and A, I'm going to give you an N by the previous argument, which is in between. And that's impossible. So there is no way for T to be less than A. Therefore, the area of the endergon has to be greater than T. So therefore, there's no way that T can be less than A. Exactly the same argument from up above. Now where T is above A, I'll find an endergon, an exterior endergon closer than that, and I've reached the double conclusion. Okay? So this is the proof by reductio ad absurdum. Here's a double because he's got to show both. And this proof is very, very familiar to people who studied Euclid. One of the powerful proof techniques. Remember from our history, it was Hippocrates is the one who's attributed to be the first one to use this kind of a proof. Okay. Again, the logic is very nice. The logic is you want to prove A is true. Assume A is not true, and go down a series of deductions. From not A, you prove this, you prove this, you prove this, and all of a sudden you prove something which you know is not true. You show something which is impossible. That means that what you started with, not A, had to be false, and therefore A is true. Okay. Let me go on and not take any questions on that proof. Let me finish the spiral, and then we'll stop, because then we're going to start the second half of the presentation. Let me just finish his work on the spiral, which is also very, very beautiful work. The Archimedean Spiral. Probably have all seen this somewhere or other. And it kind of looks like this, that's spiraling out. This would be one revolution of the spiral as it continues to go out. It kind of cuts off this amount of area. Archimedes will have something to say about this area before we're finished. But let's take a look at how the spiral is created. But before we do that, let's just take a look at the first construction I want to show you. He creates the tangent line to the spiral after the first revolution. Okay, the spiral starts here. We go through 360 degrees all the way around. And at this point here, he wants to draw a tangent to the spiral, not to the circle. Okay, the tangent to the circle is straight up and down, right? We know that the tangent to any circle is always perpendicular to the radius. If you want the tangent to the circle, it's here. He wants the tangent to the spiral. And he constructs the tangent of the spiral. That mention how that's done in a moment. And he creates this figure. He takes the tangent line to the spiral after one full revolution, and then draws, using the diameter here at the center, he draws a line straight down, and he sees where these two lines cross. He constructs the tangent. This line, of course, he has for free because he's working with this central spiral that's going around in a circle. And he can create this point T, okay? How does he create, before we get to this construction, I want to show you the spiral and show you how he finds the tangent line. Okay. He proves that this is the tangent line using very, very formal, fancy geometry. I want to show you how he intuitively shows what the tangent line is, how he convinces himself intuitively that that's what the tangent line is and where this goes. So let's take a look at the animation. I think we are here. The only other place where motion is used in Greek geometry, I've already shown you. That was that tractrix, that moving, the line moving straight down and the radius line moving down simultaneously, and where they cross created that tractrix. We don't see this again until Archimedes, where a moving figure creates the curve. We see it here the next time, basically about 200 years later, in Archimedes' spiral. What he wants to do is he wants to have a line getting longer and longer. I'm sorry. He wants to have a line spinning around in a circle, around and around and around, and a point on that line moving further and further out along his spinning line. So this line of his is spinning around in a circle, the black line, and this point is moving out further and further and further as it spins. And from these two motions, he creates the spiral. He creates the trace. Very pretty, huh? The definition of the curve, the inherent definition of the curve is this motion. It's a combination of these two motions. And he's going to study the properties of this curve. Okay? The tractrix wasn't very much studied during Greek times. It was used basically to trisect the angle and also to double the cube, but it really didn't find much else use. What Archimedes is going to do with this curve is quite remarkable. So it's a very pretty curve. And I want to show you how he intuitively finds what the tangent line is at any point. He's going to go ahead and prove it formally using very formal Euclidean geometry, very formal complex proof. But this is his intuitive idea of where to start, that he knows the answer, and then he can go ahead and find his proof. And this is a milestone in mathematics. Let's take a look again at our spiral. Okay, here I'm just helping us see it more. We're spinning out this line. This line is creating this angle, getting bigger and bigger all the time. So I'm keeping track of the angle, and also I'm keeping track of the circle. And I'm keeping track of the tangent line. Okay, this is Archimedes' tangent line. Notice this is not the tangent line to the circle. Look at that. Goes right through the circle. It hits right through. This is the tangent line to the curve, to the spiral right at its end. Okay, this is the tangent line that just touches the spiral at one point at the end point that we are in the construction so far. It is clearly not the tangent line to the circle. Remember, what would the tangent line to the circle be? It would simply be a line perpendicular to the radius. It will be a line like this. So what we're trying to track here is the tangent line to the spiral. And that's what it looks like. Okay. How does Archimedes see this? This is the first time in history anyone does this. Archimedes sees the spiral as moving out this moving point, and he sees it as moving in two different directions simultaneously. He sees this point moving out this way because he knows the line is growing longer and longer, but it's growing at a constant rate. The line is getting bigger and bigger at a constant rate. So the speed at which the point is moving out is at a constant speed. This speed does not change, okay? This arrow, the red arrow, is detecting the speed as it moves out. This arrow does not change. It's always that same constant speed of the rate of change of the length of the arrow. It's also moving in this direction because it's being turned in a circle. And the direction is the direction of the tangent to the circle, which we agree is perpendicular to the radius. It's also moving in this direction simultaneously. But this speed is getting faster and faster. The black arrow is getting longer and longer. Why? Not because this thing is turning faster, but because the line is getting longer and longer. And you spin a rock on a string, if you spin it on a short string or you spin it on a long string at the same revolution, the rock on the long string will be going faster, much, much faster, because it's going in a much bigger circumference in the same amount of time. So the black line, the velocity in the other direction, perpendicular direction of this ultimate point on the spiral, is getting faster and faster as the line gets longer and longer. And what Archimedes is saying is, if you want to know what the tangent line is, it is the combination of these two speeds. And we will not see this again until Galileo. No one will use this idea again until Galileo. And it's not clear that Galileo knew this. Historians think that Galileo had to reinvent this idea all over again, because it's not clear how much of Archimedes' work was actually known in the 16th century. It's not clear how much of it was translated, how much was translated properly, how much was still lost at that time. It doesn't seem that Galileo knew about this kind of a construction that Archimedes used. This is Archimedes' contribution to the differential calculus. Okay, this will lead, if you continue along this line, and this is exactly where Newton goes. This is how Newton sees how all of his curves are created. All of Newton's curves are created by a moving point. He's a physicist, right? He creates his curves by a moving point. We first see this in Archimedes. And notice that as the black line gets longer and longer, look how the tangent begins to favor the black line, because what is the tangent? The tangent speed is a combination of this speed and this speed, or if you like, this speed and this speed. As the black line gets longer and longer, the speed is going to become more and more dominated by the speed of the black line. So the tangent line is going to bend closer and closer to the black line because this is making a smaller and smaller contribution. This is how Archimedes sees what to prove now using his formal fancy geometry. He now knows what the answer is. He sees it by the motion of the point as being the simultaneous motion in two different directions coming from the definition of his locus, which is itself a motion. This is really very exciting stuff. And like I say, we don't see this before in history, and we don't see it again until the beginnings of the calculus. Okay, let's go back now to that last slide and show you what he proves. Okay, we now have the tangent line. All right, but look at what he's got here. Oh, I'm sorry, I need to. By the method of exhaustion, he proves that this line here, he's got his tangent line. He draws this innocent radius line, diagonal line, if you like, and just extends it down until it finally hits his tangent line. It's got to hit the tangent line at some point. He extends this line down from the center of where the spiral is starting from. He just extends this line down very innocently until it finally hits the tangent line. And he shows that this line is exactly the circumference of the circle. He shows that this straight line is the length of the circumference. And this is a rectification of a curve. Yes, it is the simplest curve of all. Archimedes is starting from the beginning, but this is the first time a curved line is pulled out into a straight line. It's constructed. The line is constructed of the same length. The straight line is constructed the length of the curved circumference. He does this by constructing the tangent line and by innocently drawing the line for the intersection. But from proposition 1, look what triangle he's made. He's made a triangle of a base of the circumference and a height of the radius. Isn't that the area of the circle? Isn't that exactly what proposition 1 is? He has now constructed the quadrature of the circle. He's now constructed the triangle. See, it's one thing to say that the area of a triangle where the circumference is the base and the height is r is equal to the area of the circle. Oh yeah, that's proposition 1. He proves that. It's another thing to construct the line, which is the circumference of the circle. That is what he does here. He produces the quadrature of the circle for the first time in history. And just one more thing, that really nice kind of pretty gray area, the area that's swept out by that sweeping line that has at its end the point, the trace line. How much area is swept out by that line as it grows longer and longer for one revolution? Yeah, another one of those Pythagorean fractions. It's exactly 1/3 of the area of that first swept out circle. I don't know. You know, when you see, and again, we can't do the proofs of these. These proofs are quite marvelous, but they're quite involved using all, these are all method of exhaustion proofs. But when you see this stuff, when you see his results, it's like it doesn't come from the geometry. It comes from Archimedes. He makes these things true, and then he goes ahead and proves them to be so. It's like he does this by the power of his will, by the power of the beauty of his ideas, that he insists that these results are simple and elegant and beautiful. So there's a whole bunch of brand new creative mathematics in this one slide, and a lot of it does get lost and needs to be rediscovered later on. Okay, let me stop here and see some questions on the parabola segment, going to the 4/3 and some of this work here. Can I answer any questions about this?
Peter, we had an early question. I wonder if it's possible, if it's easy to bring up your very first slide.
So let me what do I need to do? Need to do this? Oh, no, I want to do that. Why didn't that work? Oh, okay. Got to hit it twice. The first going back to this slide here. Is that right, Mike? Okay,
yes.
Very good.
And the question was whether that 4/3 ratio applies to any segment of a curved shape created by a straight line.
It has to be,
or if
it has to be stylized correctly. The parabola has to be a certain way. We're actually going to get to that question not this. When we get back to integration, we'll see where this exactly where the 4/3 does work out. It's not certainly for any old segment that. Oh, I'm sorry. Wait, I'm saying the wrong thing. Yes, if you pick the good C, if you pick that good C that Archimedes wants, that'll give you the parallel tangent line, you're good. That triangle with that golden point will be 3/4 of the whole segment. It'll always be the case. Okay, yes, that is true.
And Peter, I had a question right where we left off there. And my question is whether the Archimedean spiral always has the each revolution growing by a particular amount or ratio, or whether there are different size Archimedean spirals.
Yes, very good question, Mike. It depends upon the ratio of how the line is getting longer and how fast the line is spinning in a circle. By the simplest spiral is when they're both equal. That is, the line grows in the same proportion as the spinning rate, making one revolution. If you change those ratios, if you make the line grow faster than the spinning or the spinning faster, for example, you make the spinning faster, you can imagine you'll get a tighter spiral. Yeah. And so the ratio of each complete spiral out to the next spiral out will have different geometric progressions depending upon how you play with that ratio of the length of the line compared to the rate of a revolution of the spinning.
Is an actual circle considered an Archimedean spiral where the growth outward is 0?
Okay, I can go with that. That's very much of a projective geometry kind of argument where you take these beautiful figures and take them to their extremes on both sides and to try to generalize the idea. I can definitely run with that. I never quite thought of it that way. It's very creative, I think, Mike. All right. Any other questions before we go on?
Just so that I understand the exchange you and Michael just had. So would it be fair to say that the circumference of any circle is a spiral, but not
no, Antonio, no, don't worry about that. Okay, that's
okay.
No, that's not relevant to that's a wonderful kind of imaginative speculation of Michael, which has some validity in some kinds of mathematics. We can't go there. All right. We do want to go, however, to the main event. Last piece of this slide. This spiral was, as you can imagine, very, very much captured the imagination of the early calculus people. And they went ahead and applied the rectification, the lengths of the spiral and the areas by doing, new kinds of integration, not doing this and showing the 1/3 circle and all this stuff. This is from one of the great Bernoulli brothers, one of the early founders of the calculus. You could imagine these kinds of things that Archimedes was able to prove were proved all over again once the calculus was developed. And you'll see all this kind of stuff in that 1,000-page Calc 1, 2, 3 textbook that you get. Okay, last little thing before we start the main event, which is the sphere. Archimedes also gives us a way of trisecting the angle. Remember, the tridextrix was the way, the moving point. Well, he's also going to use his spiral to do this. And here he's just really playing around. I mean, this is kind of like nothing to him. But if you take a look at any arbitrary angle that you have, here's the angle AOB, and here's a spiral being spun out. This is just the formula of this spiral. It's just here in the slide from the internet. Didn't want to erase it. This is just the polar form for those of you guys who remember polar coordinates. Not important at all. So here's the spiral being spun out, and we have an angle. How is Archimedes going to find 1/3 of this angle? Well, remember, as the angle spins out, this length is growing longer and longer in the same proportion as the angle is getting bigger and bigger. So if you take this length of where of your interested angle hits the spiral and take 1/3 of that and bring that angle down to the spiral, then isn't it the case that if this length here is 1/3 of this length here, then isn't this angle 1/3 of this angle here? Isn't this how the spiral was constructed? The spiral was constructed by having it grow out longer and longer, F to E to P, in the same exact ratio as the angle is sweeping out from this angle to this angle to this angle. So isn't it must be the case, given the construction of the spiral, that this must, if this is 1/3 of this length, then this must be 1/3 of this angle. Okay? And that's all that this is saying. I just said in words what's there. And let me show you the very pretty animation. Is this what I want? I think so. Yes. Here I have blown up the spiral just for a half a turn. This is the Archimedean spiral. I've just blown up just for the first 180 degrees. And let me just show you the animation first. Okay. Here's our spiral. Here's our blue points growing longer and longer, spinning out. Nothing up my sleeve here. This is the Archimedean spiral, but I'm keeping track of 1/3 of it. Okay. And if I keep track of 1/3 of it, then it's very easy for me to keep track of 1/3 of the angle as it spins out. Okay. Very, very pretty. And so if we take an angle that we know, like for example, an angle of 75 degrees, this will be 25 degrees, 1/3, because the blue line is 1.3 something and the red line is 1/3 of it. Okay. And so we get another construction far away from compass and straight edge. Okay, this is not a compass and straight edge construction. That's impossible. But here, Archimedes really just playing around with his spiral shows another way to trisect an angle. Okay. He does this in his sleep. All right. The main event. We're going to do two things. First is probably the most famous, is his calculation of pi to I think three decimal places, or did he get 4? I forget, 3 or 4. And this is a first in history. This is the first time we get actually pi calculated to 3 decimal places, but more importantly, he shows how to do it. He shows the method to do it, so that this method can be extended if you have more patience than he did, or if you have a better algebra mechanism than he had available to him, to extend his method further and further. It is a method of how to calculate precisely the irrational number pi to any decimal place that you like. Okay. So we start off with some facts that we know that the definition of pi is an anachronism. The number pi, the symbol pi, is not used until 1700, I think. But this number that we now call pi is certainly a number known to all the mathematicians of the ancient world. We'll just, for convenience, call it pi. We know that the definition of pi is the circumference over the diameter. That is the very definition of what pi is. It is this constant ratio, no matter what circle you pick. Pick any circle you like, take the circumference over its diameter, you're going to get the same number. Call it pi. In Euclid Book 12, he proves that the area is proportional to the radius squared. Okay. Proposition 1 is going to show that that proportion is also our number pi. Let's prove this. We have this formula. This is the definition of pi. Pi is equal to, it fits the formula, circumference is equal to pi times the diameter. Proposition 1 of Archimedes says that the area is equal to 1/2 the radius times the circumference. You see where I'm going to go. I have a formula for the area. I can write the circumference in terms of pi. There's got to be a way to write the area in terms of pi. And yes, I can. The first thing I can do is take the circumference and write it as pi d. The next thing I can do is take d and write it as 2r. And the next thing I can do is multiply 1/2 times 2 and get 1. and get the area is equal to pi r squared. Although you will not find this formula in Euclid, it is implicit in Euclid's work, because once we have the area is equal to, the area is equal to something times r squared, then that something does have to be the same something as the circumference formula. It's not a coincidence that pi appears in the circumference and the area formula. It is the same fundamental constant. Okay, so he's going to prove this inequality. This is the inequality that is still used today in middle school to approximate pi. Way he's going to do it is this business of the perimeters. He's going to take the endergons inside and the endergons outside, and he's going to squeeze pi between these perimeters closer and closer until he just runs out of energy in doing this, because the way he has to do the calculations is very, very laborious. And he's going to get this computation here. He's going to start with with 6 sides. Actually, I'm going to start with 3 sides. He's going to go out to 96 sides, and he's exhausted. He can't double 96. It's just too much. It's too much work because of the algebra he has available to him. And he does trap it between 3.1408, blah, 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 and 3.142. So he traps it between, to the second decimal point, 3.14. That may not seem very impressive, but what's more impressive is the method in which he uses, because if you can go with 96 sides and start doubling that, this will just get better and better, continuing to use Archimedes' method. All right, so let's see the method. Starts with a circle of radius 1, the simplest circle you can do. And he builds the simplest endergon, a triangle, an equilateral triangle inside and an equilateral outside. He finds the sides of each of these. We'll take Archimedes' word for it, that he can calculate these sides. And the side inside, the little s, is radical 3, and the side outside, big S, is twice that, 2 radical 3. Well, then the little perimeter, which is 3 times the little side, that's got to be less than 2 pi. Clearly, this distance around, all the way around, is less than the distance here. And that 2 pi is less than 3 times the big perimeter. Clearly, it's bigger. This distance here is smaller than the distance all the way around. So he's trapped 2 pi in between the little perimeter and the big perimeter. If we divide everything by 2 and use the numbers that he uses, for the first approximation, we get this. Not very impressive. We don't even see 3 here with 3 sides. Okay, he's just getting started. He goes to 6 sides. Here, I'm only going to do the inside now, guys. Archimedes, the genius that he is, finds a way of calculating the new perimeters from the old perimeters. Yeah, he finds a progression. He finds that the new big perimeter, P6, depends upon the little perimeter right before, the little perimeter at 3, and the big perimeter at 3, according to this formula. Don't ask. Okay? We don't have time to show this. But he finds the big perimeter in terms of the 2 little perimeters. And then, very interesting, he then finds the little big perimeter, the perimeter at 6, using the little perimeter and his new big perimeter. He actually needs the new big perimeter to calculate the little new perimeter. Okay? I don't know what to say. This is what he can show. Well, once he's rolling now, he can go ahead and calculate these numbers from the little perimeter. Okay, he's got a progression to use. By the way, the little perimeter of 6 is the one easy to see. It's the only easy one to see, guys. When you have a hexagon, right, then you have a interior angle of 60 degrees. That makes this an equilateral triangle. If this is an equilateral triangle and we know the radius is 1, then this guy has to be 1. And therefore, the perimeter all the way around is 6. Okay, that's why his little perimeter is 6. It's the only easy number that we can see of the whole thing. So I wanted to point it out that these numbers are in fact not magic. If you were really to follow Archimedes' progression, you would agree with him that these are the numbers. And he goes ahead and he calculates the number, divides by 2, and he traps pi a little bit better. And at least now, for the first time, we see the first digit. We see the whole number up here. And he keeps going. Here's our first set of numbers. I just showed you that 2.5 and the 5.1. Here's 6 slides. Here's that even number of 3, and there's that 3.46. He then goes to 12 sides, I'm sorry. Pretty soon, these sides are going to get so small that it'll just blur in. But you can see how we're getting better. 24 slides, he does this calculation using that progression. We've developed a 3.1, 48 slides, and finally he stops at 96 slides, literally out of exhaustion because, yeah, Mathematica can do this very easily. He has tremendous amount of calculation. He's constructing these, and he has a very primitive algebra to work with. But the method is there. And you can see that he does get pi to 3.14, something or other. It is the method that is what is really, really important. Okay, so we are really, I'll keep this open if we need to, but we're really finished with this. And so there's his ultimate. And here's a little bit of history of where this comes from. Remember, again, to the earliest times, pi was known to about 3. The Egyptians turned out to use 3.16. This is anachronism. They wouldn't write it this way, but the way they write fractions, if you turn it into a modern decimal system, this is the number that they use. Here's Archimedes' number. The famous Ptolemy, the great astronomer, he used a different method. Didn't use the angle, the interior polygons. He uses trigonometry to get a better approximation. And then these different sides are being used. People picked up on Archimedes' method, but with a more powerful algebra, they could use a much, much larger series of sides. Okay? They could use sides to 2 to the 30th because they had an algorithm that gave them, you know, what the area and the primitives were to 2 to the 30th. They just could plug in 2 to the 30th from this algorithm blindly. They weren't actually doing the kinds of calculations that Archimedes was doing. These calculations are still very, very tedious and difficult to do. But you can see the number of decimal places is growing pretty well. Then there's a jump. People stop using this, and here is no coincidence that this is the invention of the calculus. And once we have the invention of the calculus, is one of the pioneers of the invention of the calculus, Gregory, and he started using a new method in the calculus of infinite series. And you can see where right away he begins to double the number of decimal places of pi. And this goes on, and this is kind of a milestone here. In 1870, oh, by the way, yeah, here it is. In 1706 is the first time the letter pi is used to symbolize this number. 1706 is the first time where we see someone use the word pi, and it stuck. Seemed to be a good number, and there it kind of stuck. This is a kind of a milestone in the history of computation. This fellow here devoted his entire life adding up infinite series, one term after another. Just keep going with this series, adding another term and another term. He had the progression. He could reduce the next term relatively easily, but to add that term to what he had so far is getting more and more difficult. He would do this his whole life, and he got out to 770 decimal places. And this was until the invention of the computer. This is considered the largest single computation ever done by hand by this man Shanks in 1873. People just did not do anything beyond this kind of a labor of literally doing manual calculations without a computer. You can see once we get to
Peter,
yes.
What else was Shanks doing with his life while this was going on?
I don't know. He's a real weird guy. You want to Google him. He's a weird guy. This guy. But he was a mathematician. I think he was could have been an amateur math. He probably was an amateur mathematician. I did look up him, but I don't have anything in my notes about him except the fact that this is the largest manual calculation ever in the history of math. You can see where the number of decimal points jump in the computer era, the first big computer, the ENIAC, and then the first so-called supercomputer in 1967, the Control Data Corporation's 6000 series, where you get 500,000 decimal places. The supercomputers of today, by the way, guys, now you don't worry about how many decimal places. They now use the calculation of pi out to trillions, trillions of decimal places to measure the speed of the supercomputers. My supercomputer can calculate 5 trillion decimal places of pi in 2 nanoseconds. Well, my supercomputer can calculate, that's what's happened to the calculations of the number of decimal places of pi. It's now used as a benchmark of how many trillions you can measure in a wink of the eye to
Peter,
bragging
so is that argument only between male mathematicians, or do female mathematicians
who's bigger than
participate in
who?
it too?
Sounds it. It definitely sounds it. I think women are too mature for such kind of silliness. Okay. Well, as I look at the clock, I
I have a related question to what we just discussed.
sure.
Or the last comment. So who was feeding Archimedes and doing his laundry while he was sitting and thinking about math?
Yes, I just don't know. Someone will have to Google him again and do a little research about him. I think he is kind of a character. He must have been a character to do such a thing. Okay, I look at the clock, guys, and we have 5 minutes left. And this actually is the most exciting part of this presentation. Let me just introduce the idea here. It looks like we're not going to get as much to the course as I was hoping. This is a occupational hazard of teachers. If you've ever taught anything, you know it well. I had an envision of what I could do in 8 classes, and I'm not going to make it. And my only excuse is the title of our course is Conceptual Calculus. So yeah, this is not Calc 1. I never promised it to be Calc 1. We're not going to get through even the ideas conceptual that I wanted to get through. I'm going to try to supplement it by, I think, these wonderful videos. The wonderful videos will be going through the same material that I would have liked to have gone through. That clearly we're going to run out of time. We only have 3 classes left after this. But what I want to do as a teacher is I'm not trying to teach Calc 1. I really don't care about the algorithms in the 1,000-page calculus textbook. At this point, I'm confident, guys, that you could, if your algebra is strong, you could now walk into Calc 1 over in the math department at Keene State, or walk back in if you've already taken it, and you now understand conceptually of what this calculus is about. I think I've actually attained my goal. I've given you the idea of what these tangent lines and what these areas are, and what the derivative and what the integral is about. And what calculus is going to do is show you how to do this with all kinds of wonderful complex functions, and using those functions, how to solve all kinds of incredible problems of the world in physics and chemistry and everything else. That's what 3 terms of calculus does. My goal was to try to give you the proper introduction to that, which generally is not done in calculus. It's kind of done so quickly and so half-heartedly that you get into the problem solving that you say, what the heck? What is, I tried to fill in that gap. This is all, guys, in defense of myself, and trying to stay with what I want to continue to teach. I think this is more important and more interesting than rushing or skipping this and teaching the sum rule and the product rule and the chain rule of derivatives. This is not whatever my intention was. Yes, I'm not going to be able to maybe take a second look at the fundamental theorem. Okay, we're not going to be able to take a look at that, but I'm going to show you videos which will take a look at that. 2 and 3 other videos which will present the ideas better than I could. But what I want to present in the work of Archimedes, you will not find. Okay, I take pride in this particular presentation. I've pulled together my life's work of studying Archimedes in its detail and all the glory and all the stuff that dazzles mathematicians. And I've tried to condense it down something to present to you, my class, my audience, knowing what your, what's describes your knowledge of math and trying to show you its beauty and its power confined to the math that I think we can handle. And I think that's an accomplishment. And that's what I want to do. And this is the heart of it. This method of Archimedes was not discovered until 1905. This is the greatest, most exciting discovery in ancient mathematics ever. To take the genius of ancient mathematics, the greatest mathematician of the ancient world, and generally by all mathematicians considered one of the three greatest mathematicians of all time, and discover a piece of his work which shows how he thought about these problems of integration, what he thought conceptually, how he found his theorems, and then he went ahead and used the formal method of exhaustion to prove it formally. This was just his conceptual idea of how to see what the answer was. And then, as he says himself, then I had to go really prove it. I want to show you this conceptual idea of Archimedes. It uses the law of the lever, which is like, takes your breath away, but it also anticipates the indivisibles of the calculus. The people who had to reinvent this, Cavalieri is the most famous, this forerunner of the integral, by taking those rectangles and making them infinitely small. Yeah, they actually thought they were working with infinitely small rectangles. That's what these guys in the 17th century thought they were doing, for a while at least. They had to rediscover this because Archimedes was doing this 2,000 years ago. But he wasn't doing it the way Cavalieri and Leibniz, for example, was. Cavalieri and Leibniz, they said, well, this is good. Look at this. I've got these infinitely small triangles. And look, I can add them up and it works. Great for me. I've just proven. Archimedes says, no, you haven't proven anything. All you've done is shown that, yeah, conceptually, yeah, maybe, it's like it. Now you really have to. Archimedes held himself to a higher standard of mathematical rigor than Newton and Leibniz and all of those characters of the 17th century. He was far ahead of them in terms of how mathematics had to be conducted. This is probably one of the most incredible things about him, that he produces all this incredible creative mathematics, and he's using a level of mathematics which is of a more pristine level than the great inventors of analytic geometry and calculus. And let me end the class by reading something from a quote from him. I'm sorry, not from him, but from the great mathematic historian of math, Heath, who's translated all the Archimedes and translated Euclid and Apollonius. He's the great translator of this thing. He sums up Archimedes' work in this way. Heath says, the treatises are without exceptions monuments of mathematical exposition. The gradual revelation of the plan of attack, the masterly ordering of the propositions, the stern elimination of everything not immediately relevant to the purpose. The finish of the whole is so impressive that in their perfection as to create a feeling akin to awe in the mind of the reader. And I can tell you that firsthand. And when I think next week, when I show you how he does, we're going to look one more time at that 4/3 area of the parabola, and we're going to look at the volume of a sphere. I think you will be awed by the creativity of this man. Of where does he come up with this? What kind of mind comes up with this? And the fact that it was lost for 2,000 years. Mathematicians speculate, imagine if it wasn't lost. Imagine if the later Greek geometers, imagine if the great mathematicians of the Islamic era, imagine if Descartes and Fermat had this work. Maybe, math would have been so much accelerated in its history if we had seen what Archimedes was doing here. That's how monumental this piece of work is for us. So don't miss next week. We will certainly finish this and go on to the next presentation, which I've already given you, but I don't want to skip the work in the method.
Peter,
Okay,
one question.
any question
Peter?
before we go?
Yes. So you just sketched out my question about in what way was future mathematics, I'm talking future from Archimedes, hobbled by the fact that this work was not discovered. But so what was his influence in the development of mathematics from, Galileo through Newton and Leibniz and everything else that did come through, that wasn't lost? What were the threads that?
It's a good question, and it's very easy to answer. Who's speaking, by the way?
This is Carl Sherman.
It's a great question, and it's very easy to answer, Carl. Everything that Archimedes did that was known to the mathematicians at every era was studied just as Euclid was studied. You studied Euclid, and then if you were lucky, if you were smart enough, if you had the proper mathematical education, you went on to Archimedes. He was the ultimate. And the way you made your reputation, both the Islamic mathematicians, Galileo, the mathematicians in the era of Descartes and Fermat, the way you made your mark, the way you made your reputation was to take some area of Archimedean mathematics and prove something that Archimedes didn't prove. To take a figure that Archimedes didn't tackle, take that figure, use the method of exhaustion in his method, and show something that Archimedes didn't get to. That's how you made yourself famous. That's how you made yourself credible, by being able to be in the company of Archimedes. Galileo calls Archimedes the divine Archimedes. That's how he refers to him all the time, because he seems like a god. He seems to so tower over everyone else who, in the room. So his influence is absolutely enormous in every aspect of mathematics right up to today, because all math majors study his work. Every math teacher makes sure you are exposed to his work, because it's one of the great monuments in the history of thought. Okay, with that, I'll let you guys go. See you next time.
Thank you.